My email is ronaldopintoaft.com. And today I'm going to be hosting today's webinar, and we're going to be talking about AFT Fathom's add-on modules XTS and GSC. If you have any questions during the webinar, we're going to have at the end a session of questions and answers. You can type your questions in the dial box and go to webinar, and I'll go question one by one, trying to answer them. If I don't have an immediate answer, I'll be sending you a mail with a response. So let's start talking about a Fathom XTS module. As you know, AFT Fathom does a steady state analysis. While steady state modeling answers many design questions, some questions cannot be adequately answered without considering how the system behaves over time when submitted to a varying operating sequence. Is there any undesired process condition during the transient? Does the pump cavitate at any time? How far from the VP point does the pump operate? Are there any control issues over time? How long does it take a tank to fill? What is the total pump energy consumption over time, varying operating sequence? The AFT Fathom module XTS answers such questions by modeling transient time system behavior through extended time simulations. What XTS does, it extends Fathom's control modeling capabilities to include overtime system response from a remotely controlled locative variable. For example, if you have a valve closure on a specific time schedule or in response to events in the system such as a tank liquid level. Tanks of finite volume can be specified so draining and filling can be simulated. This is one of the capabilities of XTS. The XTS module can be described as using a lumped quasi-static approximation time in simulation. What it does is it takes picture over time as a operating sequence event happens. Transient behavior is represented as a sequence of pseudostatic state solutions. So what is, sometimes when we talk about transient, there's a confusion with XTS and impulse. XTS does not model water hammer or surge transient. XTS does extended time simulation, also referred to as slow transients. This method is applicable to transients occurring slowly enough that the effects of inertia, wave speed, communication time, and pipe stiffness can be ignored. Water hammer and surge is also referred as fast transients. These transients are dominated by the physical phenomena of fluid inertia, wave speed, communication time, and stiffness of pipe and components. To model water hammer and surge analysis, you use AFT impulse. Now, XTS, there are four types of ways to initiate a transient. There's a time-based transient that are based on absolute time. Single event transient are initiated by one event such as a pressure tank, liquid level, or other parameter at a specific location. Also, you have dual cycle events, initiated transient in repeated cycle based on two event parameters, like a check valve that goes back and forth. That would be a cycle event. Dual event sequentials events initiate two transients that do not repeat, one after the other. So now, in XTS, there's junction with inherent event logic. There are two junctions types in XTS which have built-in or inherent event logic, like check valve or relief valve. So you don't. The user does not need to specify the nature of events. The program will model for them. Once you do modeling in the event results, there are event messages reports in the output windows. There are two types of reports, one sorted by time and one sorted by junction times. Like here in this report, we have 3 events that happen. The valve junction 6 triggers at 11 minutes. The other junction 3 triggers in 13 minutes. And pump junction 2 triggers in 16 minutes. So this is a report event by time, but you can have it by junction. And the report is, here's pump, the pump junction 2, valve junction 3, and valve junction 6. So when you start an event, and we're going to see an example right now that we're going to start working with, which is the valve closure. But before you start any event, you have to activate XTS. If you don't, you won't be able to simulate it. To activate XTS, you go to analysis and you select time simulation and you select transient. This will activate tabs in the junctions that will allow you to simulate the transient times in the XTS event. So the example we're going to be working with is called a valve closure. And what we want to do is the process of filling a tank located at 200 feet of elevation needs to be analyzed. It is decided to close a valve when the liquid level in the upper reservoir, J4, reaches 15 feet. So we want to close this valve when the reservoir, the liquid level in this reservoir reaches 15 feet. From the steady state run, we have estimated that it will take 35 minutes to reach this point. So we're going to model, in this case, a time transient event. Valve closure is specified in the specification window in the transient tub. We select time because we're modeling a time event, the initiation of the transient. In the transient data table, we need to provide the C sub V data of the valve. So at time 0, we have a C sub V of 100, which means it's open. At time 2100, which is 35 minutes multiplied by 60 seconds, which would be 2100. That is the estimated time we have from the steady state that it will fill. We still have the valve open, and when it reaches 2130 seconds, because the valve requires 30 seconds to close, the C sub V would be equal to 0. So what we do as we're simulating a time event, we select in transient in the valve, in the transient tub, we select time, and at time 0, it will be open. So now at 2100 seconds, which is 35 minutes, it will still be open, and it will close in 30 seconds to C sub V equal to 0. So this time event will activate it at 0 seconds. Once you specify the transient event in XTS, a T will appear in the junction that has the transient event. So here we have a T event of the valve that will close when to limit the level supply to the tank. So it's going to start at 0. Once you have specified the transients, then you go to the transient control and analysis value, and you specify for how long you want to model the event. Here, we're going to do it we're going to start at time 0, and we we're going to stop the modeling at 60 minutes. You can do it for a year, you can do it for a day, you can do it for a month. And the time step, you're going to set it based on the event. Here, it makes sense to take a time step of 1 minute. But if you're going to do an event that lasts 1 year, it wouldn't make sense to do a minute. Maybe it would be better to do it every hour or every 12 hours. So here we're going to do a time step of 1 minute, and we're going to save the output every time step. You can select not to do so and set your own time to save the event. And here you would say how many events you want to save every two. Here we have it. You would do it every 2 minutes, but you can select different if you want to save, not to take so much space, because the more time you save, the bigger the file will be. So as a result, in the program, if you right-click, you can display a quick graph of what's happening in the junction. So we right-click at the reservoir in the transient event height, and we see that J4 starts at 0. This is when the tank starts filling up, and increases over time the level of the tank until it reaches. But note that when the valve closes at 35 seconds, it reaches only 13.91 feet and not the required 15 feet that we estimated. So now we're going to go and select another option that XTS has to save time, which is an event transient and not a time transient as we previously did. For a valve closure example, instead of estimating the time of the liquid level reaches a specific value, an event transient will be initiated and the valve closure based on the liquid level of the tank. This simulates a liquid level control valve actuated based on the signal from the liquid level sensor of the tank. So now the valve is not going to close triggered by time. It's going to close trigger by the level of the tank in J4. So now we're going to set a single event, and this single again is going to be triggered by a variable that's called the reservoir liquid level when it's greater than 15, and it would be junction 4, which corresponds to the tank and the uphill. Then we specify how the transient event is going to happen. So since it's an event, it's a single event that's going to be triggered by the height of the tank, of the liquid level of the tank, then we have here that at the event of the initiation, the valve will open, 100 will be open, and the steady state value specified in the loss model. It closes in 30 seconds. Hence, the data point in 2 is 30 seconds. So you notice here that the event here is 0 time and not 21,000 seconds that we had before. And it's going to close in 30 seconds. The SysV value would be 0. So now we see that the reservoir transient tab shows that the liquid height in J4 reaches 15 feet at a step of 39 seconds. So now it worked properly. So at 35 seconds, we have, which corresponds to 2,340 seconds, we have the liquid level of 15 that was reached here. That is what we want when the valve closes. So in summary, to turn on the transient, what you need is to turn on the transient calculation using the analysis time simulation menu, define the transient or transients we wish to model, specify the start and stop time at the step size of the analysis transient control. These are the 3 steps that we need to do. When XTS transient mode runs is completed, results are displayed in the output similar to the steady state runs. Pipe and junctions up to output tables can only be displayed data for 1 step at a time. Initially, the first time step is displayed, and the slide bar and buttons in the button of the window allow the user to adjust the currently displayed time step. So here, when you see the output in the XTS, you will have the results, and this slide bar, if you move it to the right, it will change the time that you're seeing the results at. So here, the slide bar was moved to 20 seconds, and this is what you see in the results of the tab. That is one way of seeing the output. Also, there's a tab for each element. The transient tab shows the results for all time steps. The first number in the left column is the pipe junction number and the minutes. So here, we have the list of what's happening. Like here is 0 seconds, 2 seconds, 3 seconds, and so on. So you can see how the variable changes in time as the time progresses. Transient tables can be expanded or collapsed to improve the viewability. Double click on the span. So here is a plus sign. If you select it, it will expand the results, and you can see the results over time for all the variables that you want to see in the junction. Also, in the visual report and the XTS gives you data will be displayed at a selected time, the same thing. So in the visual report, you have the sidebar, and here you have 20 minutes. And if you move it forward, it will change the results shown in each member and the pipes and the junctions as you move the sidebar to the right. Okay, so now let's see an example a little bit more complex. Oil with a specific gravity of 0.8 and a viscosity of 500 centipoids is transferred from a storage tank to a tank farm consisting of 3 tanks. So we're going to see an example here. We're going to transfer oil from this tank to a tank farm with 3 tanks in a tank farm. All pipes are scheduled 20, ANSI steel with the pump junction 24, and all pipes are 16 inches. All junctions elevation is 750 feet. All tanks are vented to atmosphere, and tank dimensions are as follows. So these are the dimensions of the tank. Liquid height is 40 feet. In the storage tank is 0 because they're empty. And the tank height, total tank height is 40 feet for each. The area of the tank is 3,000 for the storage tank and 300 feet square feet for the tanks in the tank farm. Shut-off valves are located near each tank and are full open at 10,000 CSV, and the transfer pump has the following curve data. So this is the curve data. This would be the pump curve. This would be the pump curve, and this would be the efficiency curve. So we want to establish the following control logic to be implemented. Tank shut-off valves. Tank shut-off valves to close when the liquid level in the respective storage tank reaches a maximum of 39 feet. A preliminary inspection concludes that the storage tank 3 will be the last online. To avoid excessive line velocities during this stage of the transfer process, pump speed is to be reduced to 85% if velocity in the storage tank 3 supply exceeds 4 feet per second. So we want to determine how long does it take to fill each tank. So I'm going to bring the example. And here we have the logic that we read is the following. Each valve is going to close. This is a shutoff for each tank. So each valve is going to close to limit the fluid to each one of the tanks. So let's see. So we come here, we open the valve, and we go to the transient tab. So in this case, we select a single event that is going to be triggered in the storage tank 7, and when it reaches 39 feet, it's going to close in 60 seconds. The valve is going to close in 60 seconds. So this would be the corresponding valve in this case. If we open this valve here, it will close when tank 2 reaches 39 feet. And if we open this one here, it will reach when tank 3 reaches 39 feet. Now, there's another control logic that we want to use, and it's the pump. So we want to control the speed when it reaches it's bigger than 4 feet per second. So that would be, we're going to select the pipe 9 as our limitation on the speed. If we see that the speed here in pipe 9 is bigger than 4 feet per second, we will reduce the pump from to 85%. So if I open the pump, and I go to the transient event, I will see that I have a transient event that will change the speed of the pump to 85%. So here we have, if the velocity of the pipe 9 is bigger than 4 feet per second, then you reduce the pump from 100% to 85% in speed. We hit OK. So now all the events transients are specified in each one of the shut-off valves of the tanks and in the pump. So one of the steps we have to do before we do the analysis is go here to system, we go to transient control, and we specify the time we're going to run it. here we said we're going to run it for, we're going to start at 0 seconds the simulation. The stop time will be 1 hour. And we're going to take pictures every 2 minutes. But before I move on, I want to see if the control that I established in the pump and pump J2 is really effective to control the speed limit to 4 feet per second in this section that supplies tank 3. So I'm going to use one of the features of Fathom, that is, I come here and I'm going to establish a design alert. And the design alert I'm going to establish to pipe 9 to see if the speed of the fluid goes above the 4 feet per second and if the control is effective. So we're going to create a new design. We're going to call it maximum velocity. It's in pipes. It's a velocity. Maximum 4 feet per second. This is what we want to limit. And we come here and we specify it in pipe 9. Okay? So we say update. So now we have, we say okay. And if we open pipe 9, we will see there's a design alert of maximum velocity of 4 feet per second that is established in this pipe. So now if the control that we established to limit the velocity does not work properly, we'll receive a message in the time that it happens. So we're ready to run it, the XTS. So we go to output. And now we see that we have 2 tabs for each element, transient event and pipe event. Let's start by seeing okay, so we're going to go to the reservoirs transient, and we want to see the liquid level of the tank. So we collapse the rest. We come here and we go to 4. So now I have the transient event, and if I hit here, it will give me the list of the event for the supply tank. And this one is each one of the tanks. So if the liquid level, if I right click on it, it will give me a graph and it will let me know that it was filled in 15,000 seconds. Also, we can see the pump transient. So one of the things we want to see that is interesting for us to see is how far is the pump operating from the best efficiency point. So I'm going to click here in the quick graph. And this is the quick graph of the pump. As you know, API 610 established a limit for the pump to operate not above 120% and not below 70%. So here, the pump is operating all the time above the recommendation established by API 610, and it's operating, so it might have high vibrations because it's operating too far from the best efficiency point. Another thing that we would like to see is whether or not the the 4 feet per second limitation that we establish by controlling the speed of the pump is really effective. So we would go to transient, and we would go to pipe 9. Here we have the information of pipe 9, and if we go to velocity and we say a quick graph, we want a limitation of 2 feet per second, or 4 feet per second. So we can see here that the control is really not effective, because during an important time, the speed that we want to limit goes above the one we established, as a limitation that is 4 feet per second. So that's another one we have to see. So in the quick graph, we can see one of the questions that we had in the problem is, how long does it take to fill the tanks? So we come here in the graph and we have a transient event. So we select here and we see what we want to see. We want to see the reservoirs. We want to see tank 1, tank 2, tank 3, tank 4. We want to see the liquid lay height, and I'm going to see the graph in minutes. So we say generate. And here we can see how long it took the tanks to fill. So if I select here the cross here, tank 1 was filled in 26 minutes. Tank 2 was filled in 40 minutes. And tank 3 was filled in 48 minutes. So the total time of the process to fill the 3 tanks took 48 minutes. Conclusion. Tank 1 fills in 26 minutes. Tank 2 fills in 40 minutes. Tank 3 fills in 48 minutes. Another conclusion that we have is that the transfer pump operates very far from the best efficiency point, according to API 610 allowable, which is 120%, which can generate cavitation, high vibration, suction in the recirculation, and reduce bearing life and seal life, which would increment the cost of maintenance of the pump. Also, the control designed to avoid excessive line velocities are not effective, because we saw that the speed of the fluid was above 4 feet per second in pipe 9, which we were trying to avoid. So now let's talk about GSC. This is another very useful module. What GSC stands for is a goal sequence control. It automates the process of changing input variables to achieve a desired goal. You set the variables, and it will calculate the goals for you in the network. When a single parameter is being changed, the manual process can usually be successful when you have only one parameter. When you have 2 or more parameters, the same time quickly becomes impractical using manual methods. So this is when GSC is very useful. Although sometimes when you have a single parameter and you have a big network, it can also be a very big time consuming. You can specify goals to ensure a group of pipes or junctions satisfy an operating criteria. And this is very useful when you're doing a firefighting system design, that you have an area that's covered with sprinklers. You can group them and establish certain goals within that group, which would be a minimum flow required by the NFPA. Also, GSC can link variables to force commonality in solutions. So what GSC does is extends Fathom control modeling capabilities to include controlling a remote located variable. For example, calculating a pressure reducing valve set point that controls pressure, not at the valve's outlet, but at the outstream location. So you can also model controlling in your the control philosophy in your network and set goals for that. Goals may be single or a group of maximum or group of sum. Modeling parameters that may be specified in a variable is the variables so you can establish as a junction elevation, reservoir liquid level, and temperature, control valve set point, pump speed, flow, head rise, impeller size, spray discharge area, and K value, three-way valve, open percentage, valve loss value. Modeling parameters that may be specified as a goal is a pipe flow, head pressure, temperature, velocity, junction flow, pressure, temperature, control valve, head pressure, flow, heat exchanger, heat rate, flow, temperature, pump rate, pump head rise, flow, power, NFPA's margin. So how do you establish the variables in GSC? So you have in GSC goal seek and control you have a goal seek and control manager where you establish the variables and the goals. First, let's start. How do you establish the variables? You select the tab variables. You select a new variable. And here is a box because you can establish many variables and activate them or deactivating using this checkbox. Like here, the checkbox is selected. This means this variable will apply. Here is the type of junctions that it will apply. In this case, is the junctions. Only junctions may have variables. And here you establish a junction type. So here we're going to control the variable will be in a pump. Here's the location. Then here you establish the speed. It's a variable that you're going to change. And if you want to link it to another variable that will change simultaneously, you can do so. And here you establish the limits, lower limits or upper limits that the GSC value can move around to calculate. So then how do you establish the goals? You select the goal tab. You select a new goal. So now here we have two groups. And this box will activate or deactivate the goals you want to reach. You establish the type of goals you want to establish. Here we have a group goal, or here we have a point goal in the second goal. So we then select the object types, either junctions or groups or pipes. You can establish a different type of object. The goals parameters, like here, we establish the volumetric flow rate and the open percentage. Then here, you establish the criteria, equal to, bigger than, less than, the goal value, 600 or 500, the units, and the object ID, which is the identification of the junction. There's three types of goals you can specify. A point goal is specified when the desired goal can be specified at a specific object location in the model. Differential goal. Goal value is the difference in value between two specific object location. For example, a minimal differential pressure between a supply and a return header. The differential is defined in the object value 1 and the object value 2. So here, when you establish the goal, the differential that you want, you establish the differential between the two objects that you want. Like here, it would be reservoir J10 and the difference between reservoir J11. So once you establish in Goal Seeker the goal in the variables, a V and a G will appear in the model. Here we have a variable established for this valve, and we have a goal here. And here in this pump, we have a G and a V, which means that within itself, there's a variable and a goal to be achieved. So now when you run the program, two tabs appear in the output window, general section, Goal Seekers, Goals, and Goal Seeker Variables. So now you have a new tab that will show here the Goal Seeker Variables and the Goal Seeker Control. Also, you can create a disconnected scenario with the input values equal to the solution of the variables. So now you can create a scenario that would not be connected to the parent. And this way, the valve will be, the values that the program calculated will be transferred to the new scenario, and you can run it. So now let's work in the model to show you the feature of GSC. So the advantage of GSC is increased rapidly when you have more than one variable or one goal. So now we're going to work with this model, determine the valve position to achieve a temperature to the discharge tank of 120 degrees Fahrenheit at a pump speed and a pump speed limit to limit the absorbed power to 10 HP. System fluid is water with a temperature at 7 degrees. So what we want to do is we want to see the percentage that this three-way valve will send through the heat exchanger and through the bypass to obtain 120 degrees Fahrenheit at the junction and the connection to the discharge tank. And also, we want to limit to 10 HP the consumption of the power of the pump. All piping elevation are 8 inches. Junction elevations are 0 feet, except for the reservoirs. Reservoir liquid elevation is 10 feet and 40 psi surface pressure. Fluid temperature is 200 degrees Fahrenheit. The pump head and efficient data is shown below. So this is the curve of the pump. Heat exchanger are counterflow and loss value K is 1400. The area is 1600 square feet, and transfer rate is 15 BTU per hour. Secondary flow is 200 pounds per second at 40 degrees Fahrenheit, and a specific heat of 1.0 BTU per pound. Three-way valve open percentage and versus CSV data is as follows, and the valve is initiated to set an open percentage of 50%. So this is the table for the three-way valve. It's the same. It's when it's totally open, it has a CSV of 100, and it's the same for both passes, for the bypass and for the heat exchangers. So the first thing is to define the variables and the goals to automatically determine a valve position that will result in 120 degrees in the discharge tank. Variables in the three-way valve open percentage to limit go-see control physical possibly position range specified from 0 to 100. So these are going to be the limits that the goal seeker can move on, from 0% to 100% open. It cannot open 120 or 100, only up to 100%. The goal will be the outlet temperature at the branch junction upstream the discharge tank. So this would be the variable. And also, we have another variable and another goal that we want to achieve, and which is for the pump. So we define the variables for the pumps and goals to automatically determine the pump speed that will limit absorbed power to up to 10 horse HP. So the variable is the pump speed, and the limit, the lower and upper bounds for the limit of the pump would be 0 to 100% speed in the pump, and the goal would be the pump overall power. So let's bring the model. From XTS, from GSC. So the first step, before you do anything, you have to activate the module. To activate the module, you have here in the lower right corner a little box. This box allows you to activate the module. So we have GSC, we say okay. Then you go here to the analysis module, and the same as XTS, you have to go to Goal Seeker and use it. I'm going to erase this scenario. Then we're going to establish the variables and the goals. As we said, we have a three-way valve. So we want to see how much it shall send to the heat exchanger, what percentage shall it send to the speed exchanger, and what percentage shall it send to the bypass to obtain 120 degrees here at junction J21. And also we want a consumption of the speed of the pump to obtain a consumption of 10 HP in the pump. So to do that, we go to analysis. And we established first the variables. We go to tab, and the first variable would be in J10. So we have the three-way valve, and the variable that we want to establish is the open percentage of the valve. And the limits we want to establish is 0 to 100. We don't want it to move up beyond that. The other variable that we want to the speed, and also the limits that it can iterate to, 0 to 100. So once we set the variables and we activate both of them, we go to the goal. And the first goal would be here in J21. We want the temperature to be in J21 120. So we set a type of variable point in the branch, the temperature, the criteria would be equal to 120 degrees Fahrenheit. The object ID would be the branch, and the second variable, the second one that we want is the pump. The goal parameter will be the overall power equal to 10 HP, and then the ID of the goal would be J7 pump. So once we hit OK, we see that the program marked with the V for the variables and a G for the goals. This one controls this one, and this one is controlled within itself. We have a goal and a V in the same junction. So now we run it. So it's starting to iterate to meet the criteria, the goals, to find the variables that will satisfy what I want in my network. If for any reason it cannot reach the goals that we want, it will give me a warning message saying that that it cannot be achieved, the goals, because either it's not possible, or what I'm asking for to achieve in the variable makes no sense. So look at the number of iterations it's taking. It's taking a long time. So Goal Seeker will save all this time for you. And especially when you have more than one variable, it's very difficult to meet it. So now we go to output. Now we have two new tabs: the variables and the goals. So let's see the variables. So to reach 120 degrees, the three-way valve would need to send 83.84% to the heat exchangers, and the pump to operate at 10 HP would need to be at a speed percentage of 96.92%. The goal, since there's no warning, it reached what we want, the 120 and the 10. So now I'm going to create in a scenario with this values that is disconnected from the parent. So if I hit here, I give it a name, and I say 120 degrees Fahrenheit, column 10 HP. This is so now it created a scenario. If I check the workspace here, it has the values I need to. So the percentage that is open is 83.84. So this scenario will give me a temperature of 120 degrees here, because the percentage that is being sent and the mixture that we get here will give me the temperature that I want, and also it will give me a consumption of 10 HP in the pump. That is what I required. Conclusions. Three-way valve needs to be open 83.84% to achieve a temperature to the discharge tank of 120 degrees Fahrenheit. Pump speed needs to be limited to 96.92% to absorb power of 10 HP, horsepower. So Now we come to the session of question and answer. As you can see, XTS and GSC are very powerful. They will save you a lot of time. So let me see if you have any questions. Okay, so I have this case. When the movie of the presentation will be available, is it possible to have the presentation file? Yeah, of course. Send me an email, and I'll send you my presentation, and that way you can see the movie and have the presentation. And also, if you want the models that I used, you can I can send you the models so you can follow the presentation and do it yourself. And also, if you want a trial of XTS and GSC, we can activate it for you. So just let us know. Contact me, and we'll activate the XTS so you can do a trial with it. In XTS, what junctions can be transient? Almost any junction can be transient. The pump, any junction that you can control the any parameter like valves or well, the pumps, etc. So yes, any pump, any junction that you can control the variables by operating can be modeled. Thank you. Okay, so I think I answered all the questions. If you have any questions, just send me an email. I'm going to type here my email again. My email is, give me 1 second. Let me see how I can type it. My email is, I'm typing it right now. So here you have my email. Just send me an email, and if you have any other questions, just let me know. And again, if you want to activate a trial of XTS, GSC, or receive a quote, just let me know. So what's next? You will receive a follow-up email with the link of today's recorded webinar, and also we have it in library, so you can see it anytime you want. So also you will receive a notification of the upcoming webinars. You can download a free demo from our website, or you can request an evaluation license. For pricing information in United States, it's posted in the website. And international, contact your local channel partner to receive a quote. Thank you very much for attending today. And in 15 days, we'll have some applications, webinar with some applications, successful cases of XTS and GSC was applied, and we'll be explaining the example, the real life example. So I invite you to join us. And again, thank you for your time, and hope to hear from you.